Good morning to all of you. Let's start this class. This would be the last class on color image processing for the time being. Good morning, Ashia. So let's go ahead with today's work. In this class, we are going to talk about the few more interesting things which are left in color image processing. Typically, what is called as color image smoothening, color image sharpening, segmentation I will talk very briefly because I'm going to take another lecture on segmentation, so not much here. And noise in color images, in fact, in more detail we are going to talk about noise. That's a very important topic any which way, and for color images it becomes more challenging, so we are going to talk in detail, and then we will end our lecture with a small demonstration. So going ahead, what is color image smoothening? So remember, we have learnt smoothening in grayscale images. So if you can recall, what we did to smoothen an image was using a kernel. There are various types of kernels that we have used. We have used box kernel, Gaussian blur kernel, etc. You know how does a kernel operate? It is defined over a small region in the image plane. It computes or calculates average with weighted coefficients and changes the central pixel by the new value, and then the kernel shifts to the next region, and it continues this operation for all the pixels in the image. And that's how the smoothening kernel or any kernel work. The process, the mathematical process that we use here is convolution. So we are already familiar. Just that when you come to a color image processing, we remember we had last lecture we had seen that every pixel in a color image is actually a voxel, in a sense that it is a pixel in the image plane, but it is also a vector. It has three components, R, G and P, and it is a vector in the RGB color model. So it is a vector in RGB color model, it is a pixel in an image. Combine the two, we get a voxel. So the kernel that you are applying, the kernel in a good pure smoothening, the kernel that has to be applied has also have three components. One for red, one for green, one for blue. So typically a kernel can be defined this way, which is a very straightforward. It is defined for a small region of the image x, s of xy, and you have s and t as your running indices. They will vary depending upon how much is the region, how big is the region. This is one element, one particular element of the image, one particular pixel. S and T, it's its coordinates. You run it over all the coordinate, divide by some weighing fraction, and you get the average. So your summation will run over all, then you divide by total number or whatever, you get the average. And that's how you typically do your averaging. So averaging or smoothing now has to go in each color plane. So this can be defined for color images in each color plane. So here, when you are doing in the red color plane, you take all red values. When you are doing it in the green plane, you will do all green values. When you do it in a blue plane, you have to use all blue values. The only challenge, complication or advantage, depends how you look at it, is that you can apply an equal smoothening in all the three planes. You can also apply unequal smoothening in all three planes. So for example, I can do a smoothing of red by a 3 by 3 kernel, smoothing of green by a 5 by 5 kernel, and smoothing of blue by say 11 by 11 kernel, or I can leave it without doing any smoothing. So I can treat each component differentially. That is the advantage, more control, but that's a mathematical challenge as well. Now, what I'm talking about RGB, same is true for HSI model as well. So I can have three components HSI, and then I can apply smoothing in a very similar way in the three HSI plane too. Sometimes HSI model could be better for smoothing. Remember, because hue is taken out, saturation is taken out. Most of the time smoothing is required only for the intensity component. So here is one example. This is an image which is smoothened out in RGB plane, and this is part is smoothened out in intensity plane. So typically, smoothing reduces noise. So in both the images, the noise has been smoothened. But when you are doing an RGB and equal RGB, then you are actually losing color information. So if you do it only in the red, you will lose red color info. If you are doing in green or blue, you will lose green or blue color info. While here you will retain your color information, but you will only lose the intensity information. The results are different. So if you subtract, it's the same image processed in two different ways. If you subtract one from the other, then you can see that some part is still is appearing. If this is not a completely gray, that means the results are different. That's one of the ways how you check two images, two identically processed images, if they are same or different. Okay, let me connect my charger. So going ahead, the other process we have learned earlier is sharpening. If you remember, we used Laplacian to basically as a tool for sharpening images. Here also, the Laplacian remains the tool for sharpening the images. So Laplacian again, just like we did in grayscale images here also, but we have to apply Laplacian in three dimensions. So the color image xy, or the color vector here, voxel x up to the point xy, and if you apply a Laplacian to it, that means you are actually applying the Laplacian in all three planes, that is the red plane, green plane, and blue plane. So that is how it will work, and again it will give you edges. Remember again that here also a differential work is possible, in a sense that you can apply say Laplacian only to the red plane but may not touch green and blue plane at all. That will also give you some interesting results. Let's check an example. This image you are already familiar with. We used this for the last class. Here this image I have blurred it out a bit. If you observe it carefully, it is not very sharp. It is blurred out image. Then what I'm doing here is I'm converting it into planes. So if you observe carefully, these are the three planes. Again, I will show you. First is the red plane, then comes the green plane, and last comes the blue plane. I again show you red, green, and blue. Okay, so these are the three planes here. Now what I'm doing is I am sharpening them. So I'm sharpening the all the three planes here. Basically, I'm not doing an unequal sharpening, I'm doing an equal sharpening. So if you observe carefully, the three planes, the image looks blurred here, the three planes, they look blurred. Then here the three planes are sharpened. In fact, I feel I have made it over sharpened, but that's fine. And now I will combine these three RGB planes to create my original image. This was my original image. To create the new sharpened image, this is the new sharpened image. So you can now see the sharpening effect on a color image. You do it plane by plane. For every plane you apply some amount of sharpening, and once you have applied some amount of sharpening, you can recombine those planes to get a sharpened out result. So that is image sharpening in color image processing. Now we come to the, as I said, segmentation is an important idea where you remove or identify the important features of an image. Particularly, like you try to find out an edge, an area, a circle, or something like that. But as I said, I'm going to take another class or another lecture next week, possibly on segmentation. So let's keep it there. We have already spoken about segmentation a little bit in our grayscale imaging, where we talked about edge detection, gradient, etc. Let me focus on the noise in the color images, because that is a very important topic and many of us don't realize this. Even if you take a photo by your cell phone, simple camera, most of the photos are color photos and the noise is dominant, but we don't realize it. This noise, unlike in grayscale the noise is only in gray channel or only in one channel. Here the noise goes in all the color channels. So if you are using an RGB model, which is most of the cameras use for taking photos, either sRGB or Dolby or RGB or Apple RGB. I mean, these are the major standards for RGB. So any camera which is using one of these RGB models, the noise can get into all the three channels. And then it becomes difficult because each channel, depending upon the lighting condition, may get different amount of noise. So for example, if you are taking an evening sunset photograph which is dominant by strong red light, the red color, remember, if stronger is the light, the noise percentage in the image becomes weaker. So the red color may not get that strong noise, but the other two colors, that is green and blue, may get quite considerable amount of noise. So that becomes challenging, that different channels can get unequal amount of noise. Similarly, if you have an indoor scene, if you have an image which is using an artificial light source, and an artificial light source may be dominant in some wavelength and may not be in some other, and that will affect the noise in different channels. Therefore it is a very peculiar condition. And use of color filters, as I said, different color lighting situation, and it is very difficult to notice. Means many of us, we take that there are some colors in the image and we take it for granted. Unless and until you have little trained eyes, it will be very difficult for you to figure out the noise component. So it is very difficult to notice also. Now remember, the ideally we should average out. If you average out, the noise is filtered, that we are all familiar with. I mean, reducing noise, one of the ways to reduce noise is applying averaging. But then if you are applying an averaging blindly, without realizing which channel has more noise and which channel has less noise, you will actually lose the color information in all the channels. That becomes a useless exercise. So basically, all color noise reduction algorithms follow particularly a judgment of how much color is present or how much noise is present in each color. So some color planes where the noise is more, you apply more averaging, stronger averaging. Some color panels, some color planes where noise is less, you apply less averaging. So the averaging has to be done very wisely. I have a color image with me. This is This image I had clicked in 2009 when I had visited Ladakh. I was on the way to Pangong So, which is the site of current tussle between India and China. So this is just a few kilometers before that location. Wonderful morning light, you can see lots of mountains, but look at it carefully and you will find that it is scattered with noise. Look at this section, for example. Now this section otherwise should have been smoothened out, but you can see that there are patches. Look at these sections. Look at sections over here. And as I had told you, once the light becomes darker, the noise becomes dominant. So the noise goes on becoming dominant here and more dominant over here and here. So that becomes an issue. If I zoom in a particular portion of the image, maybe I can see I'm zooming in this part of the image, only this part, and you can see the amount of noise, and you can see that this is a color noise. It varies, red color and blue and green, all the colors are there. So this is how you identify the color noise. Now, once the color noise has been identified, the removal becomes easy. There are ways to do it. I have taken my sample image and I have split it into a RGB component and I have split it into a HSI component, both the components. You can now see very careful observation will give you very interesting inferences. You know that in an RGB, you will find that the red component has the maximal noise. The maximum noise that a component has in RGB, not talking about HSI. In RGB, red component has the maximal noise, followed by green component, which has some noise, followed by blue component, which has even little lesser noise. Maybe I would say, to me, the green component noise and the blue component noise levels are acceptable. But red component noise, no way acceptable. It's huge. Now, how is it when I split it into HSI component? So now if I split it into HSI component, then I see that the noise gets distributed in all three. It is there in the hue also, it is there in the saturation also, it is there in the intensity also. So you can see that is this model here is not very useful for me. Like here, if I try to reduce noise in red, particularly it's a color noise, I reduce in red, rest two I believe they are acceptable and I'm done. Here this spreads down on all three. It's a color noise, so it is maximum strength is in hue, little bit less strength in saturation because not all the colors are saturated. You can easily see that the colors which are less saturated, colors here which are darker, more saturated, will have more stronger component of noise. HSI intensity has the least noise in HSI. Why does it have the least noise? So if you can recall our discussion in the last class, To get the intensity image, you take an average of red, green and blue. So this is already averaged out when you are calculating intensity. Therefore, the intensity will have least amount of noise. So that is how intensity will have. So the best way to process this image is in the red component. All I can do is I can average out the red component, and once I average out the red component, I can add it to the green and blue to get my final answer. So let me see what are my results. So this is the red component after applying some Gaussian blur. So it is now blurred out. You can see that some details have also been lost, and these are the mountain ranges which are still appear. They are appearing in this image, but their sharpness has been considerably removed. But remember, I'm not touching the blue plane, I'm not touching the green plane. So those two planes will have all the data, but I'm only averaging out, or I'm only blurring the R plane. Now here is my resulting image. Now what I've done is I have blurred out my red plane. Then from the previous drawing, let me just go back. From my previous slide, from this slide, I'm averaging out the red plane, but not touching the green and blue plane. I'm leaving the green and blue plane as they are. Okay, so once I do that and I combine the three planes together to form my original image, this is my result. You can see that it has smoothened out considerably. If you want to compare with the original, you can check. You can see that the noise has been considerably reduced, much acceptable. Remember, it is a very zoomed out portion of the entire image. You can test working on this. If this is acceptable, then we can apply the same correction to the entire image and it will hopefully work out. That's how we proceed. And then finally, we go towards our demonstration. So I have the demonstration which I'm going to show you right now is the last one, and maybe if time permits I can show you some earlier discussions. This is my original image. I'm using Fiji or image J. Remember, even you can use image J for a very quick reference and quick checking. It's a helpful tool. I do it often to prepare things for my class, but once you have checked in the image J, perhaps you can always go ahead and do it with Python. So this is my image. All I can do is maybe I can open it once again. I will open two instances of my image. The second instance I will convert now into an RGB stack. So this is my red channel. This is the green channel. This is the blue channel. You can see that the red channel has a lot of noise, while this has less noise. This has much less noise. Now what I can do is I so I am keeping my original image with me here on the left, and I'm keeping my RGB image here on the right. Now what I do is I will select this and I will split it into its I will split the three components independent. They are right now stacked. This way it is a stack. So one, the three components. Yes, these are stacked components. I can remove them from the stack to individual images. For that I will use the command stack to images. So once I press this, all I will get is that is gone now. Now I'm getting the blue, I'm getting the green, and I'm getting the red. This is the red component, green, blue. As I said, I will not touch blue component. I will not touch the green component. I will touch only the red component. So by taking red component, I will go to process, I will go to filters, and maybe I will apply a Gaussian blur filter. Now I want to apply a strong Gaussian blur, so maybe I will take a 7 by 7, a very strong Gaussian blur. Earlier what I had shown you was 5 by 5. I can always make a preview and check how much blurring is happening. Do take a note. It's a huge amount of blurring. Maybe 5 by 5 help me. That's a judgment that a DIP person has to take. Some sort of noise is still there. So let it be. I will take it as 7, and if this is my acceptable, I would say okay. Now some noise is there. As a second thought, maybe I should apply some blurring in the green, which has more noise, blue, which has very little. So there I had applied a 7 by 7. Here maybe I can apply a 5 by 5 blur. I go to filter, I go to Gaussian blur, and at 7 by 7 you can see it's a lot of, everything is smoothened out. You can see all noise is gone. Do remember that at 7 by 7 in the red channel, noise is still there. So I don't need 7 by 7, rather I can go to start with 3 and see if some noise is still there. So maybe I can go to 5. 5 is okay here. And this blue channel, do I apply some? Let that be as it is. So blue is as it is. Here all the noise is gone. Here some noise is still remaining. Now I can merge the three. So to merge the three, all I need to do is I have to go to image, go to color. No, sorry. I have to first merge them into a stack. I had destacked them, the three images. I have to make a stack. So I go to image, I go to stacks, and I would say images to stack. It will ask for the name. Just put any new name or just say OK, and it merges the three. No, oh, it merged the original also. So that's a bit of a stupidity. Opening two instances. Let me just quickly redo it. Image, stack, stack to images. No, so sorry. You go to image type. You create an RGB stack first. Then go to image, go to stacks. Then create stack to images. Take them independent. Blue, green, red. Red we process with a Gaussian filter of 7. Now we know, so no need to discuss. Green we process with a Gaussian filter of, as we had discussed, 5. Okay. Now I have these three images. I will bring them back to a stack. Images to stack. So they form now one stack. One stack has now 3 images. Now I can go to color again and go to stack to RGB. So from here I will create an RGB. You can see that this is my RGB, resulting RGB. You will find that the noise has almost been removed, but applying a little stronger blurring has made the scene also very blurred. I would compare it with the original just to give the reference. There are two different ways I edited the original. One I had shown you in my PowerPoint. If you can notice, this is applying only to red channel and a Gaussian blur of 5. You can see that this is much sharper. You have not lost data, but applying little aggressively has made you lose data. So this is how all color image processing and noise removal happens. As I said, it's a challenging process. One learns only by experience. So keep practicing, keep learning, and we'll keep giving you more insights. We end this lecture. Thank you.